We plug stuff in every single day, right? And we never really think about it. But behind that simple wall socket, there's this incredible hidden engine that powers, well, everything. So today, we're going to pull back the curtain and look at the elegant, super powerful system that makes our modern lives even possible.
Yeah, every single time you flick a light switch, you're plugging into this massive grid. It stretches all the way from these huge power plants right to your neighborhood. But here's the thing, the real magic isn't just that the power shows up, it's how it's made and sent so efficiently. And that's the story we're diving into. Okay, so the power you and I use at home, that's called single-phase power. Just think of it like it's the last simplified piece of a way bigger, much more complicated puzzle. To really get the whole picture, we've got to look at all the other parts. All right, Section 1, power behind the wall, from one phase to three. So let's kick things off with what we already know, that single-phase power in our homes. Because understanding this, it's the key to unlocking how the whole grid is put together. So what is single-phase power, really? At its heart, it's pretty simple. Picture this. You've got a generator, right? Inside, there's just one coil of wire spinning around between a couple of magnets. And as it spins, it creates this single flowing wave of electricity. And here's what that looks like. On the left, you've got that single spinning coil. And on the right, that's the nice smooth sine wave it produces. But, and this is a big but, look closely at that wave. See how it goes up to a peak, then drops all the way down to zero? It does that twice for every single spin. This means the power isn't constant, it's actually pulsing. And that right there leads to a huge question. I mean, if the power is literally dropping to zero all the time, how in the world could you run giant power-hungry industrial motors with it? Or factories? A power supply that keeps cutting out, even for a millisecond, just isn't going to cut it for the heavy stuff.
Well, the answer is just brilliant. Instead of one phase, you use three. A three-phase generator doesn't have one coil. It has three separate coils, and each one is pumping out its own perfect synchronized wave of voltage. And this is the secret sauce: 120 degrees. Those three waves of power, they're not all happening at once. They're intentionally spaced out, offset from each other by exactly 120 degrees. This precise timing, this is the key to the whole system's power and its crazy efficiency.
Okay, Section 2, the star and the triangle, how three phases connect. So we've got these three awesome synchronized power sources, but how do you actually wire them all together? This is where the engineers got really clever with a little bit of geometry. Turns out there are two main ways to hook up a three-phase system. You've got what's called the Y connection, or star, and the delta connection, which looks like a triangle. And the biggest difference between them is pretty simple. The star has a central, common neutral point. The triangle, or delta, doesn't. It's a closed loop.
So let's look at the star first. See how the three sources all come together right in the middle? That's the neutral point, that little N there. It's a really clean, straightforward design.
Now, the delta is different. As you can see, the three sources are connected end to end, making that closed triangle shape. And notice, no central neutral point here. It's just a different way of achieving the same goal. All right, Section 3, why it matters, the power of balance. So we've got three phases. They're separated by 120 degrees, and they're hooked up in either a star or a triangle. But so what? Why does any of this actually matter? Well, it all comes down to one beautiful concept: the power of perfect balance. Okay, get ready for this, because this is the mind-blowing result of that perfect 120-degree spacing. Essentially, the currents from each of the three phases perfectly cancel each other out. This means that in a balanced system, the neutral wire, the one that's supposed to be the return path for the electricity, carries practically zero current. It's wild. All the power goes out to do the work, and almost none of it has to come back. And that perfect balance is what makes the whole system so unbelievably efficient. If you don't have current flowing back on that neutral wire, you're not wasting energy. It's all about delivering pure, useful power. So let's break down the advantages, because there are some big ones. First off, you get constant power delivery. Because those waves overlap, the power never drops to zero. That's absolutely crucial for big motors. Second, you get way more power density. You can send more power using smaller, cheaper wires. And finally, of course, that incredible efficiency we just talked about, all thanks to perfect balance. There's a really great analogy for this. Think of single-phase power, like one person trying to pedal a bicycle. You know how there are those little dead spots in the rotation where you're not really pushing? That's single phase. But three-phase, that's like having three people pedaling the same bike, but they're all perfectly in sync, each one starting their push exactly 120 degrees after the person before them. The force on that wheel is just always smooth, always constant, no dead spots at all.
So yeah, the next time you look up and see those big power lines, you'll actually know what's going on inside. There's this elegant, invisible dance happening in those wires. This perfectly balanced three-phase system really is the hidden engine of our world. It's what's running the factories that make our stuff, the data centers that power the internet, pretty much everything. It's just an incredible piece of engineering when you think about it. And it kind of makes you wonder, right? What other perfectly balanced, brilliantly efficient systems like this are hiding out there, just in plain sight, waiting for us to understand them?